Hey guys, it's Mr. Ray here with our next lesson in grade 12 vectors. We are working in the unit where we create equations for lines and planes in R2 and R3. Today will be the final lesson, and we're going to continue on with equations of planes, which are always in R3. And today we're just looking at the Cartesian equation. In the previous lesson we looked at vector equations and parametric equations. So you may remember that we had Cartesian equation of a line in R2. Well, this equation is similar to that, but obviously going to be different because it's defining a plane. So we've got our definitions here, the plane. Now, we're going to be talking more about the normal today, but you guys know that the normal, it will be a direction vector that's perpendicular to the direction vector of the plane. So, and we called it vector n for normal. So, and we called the direction vectors for a plane or for a line m. Okay, so m and n will always be perpendicular to each other. So that means that m dot n, dot product of m and n, will always be 0 because the angle between them is 90 degrees. So we have a normal for planes as well, but obviously now we have 3 components because it's in R3. So we have added the third component for the z direction, and it's going to be called c. So capital A, capital B, capital C are the parameters for the normal. Okay. Now, the Cartesian equation of a plane is given by this equation. So it's ax plus by plus cz plus d equals 0. So if you remember the equation of the plane in R2, it had the same first two components, ax plus by, but then it was just plus c. So, you know, we're kind of renaming c to d here because we've added this third multiple of z as the extra component because we're now talking about R3. Okay, and those capital letters A, B, and C come directly from the parameters of the normal vector to the plane. Okay, so if we can get a vector that's perpendicular to the plane, that gives us the normal, and then we've got A, B, and C, and at that point all we need is to know a point that's on the plane to figure out what D is going to be. So that's what we're going to be doing today. And there's a couple of other concepts here, nothing earth-shattering. Basically, you know that you'll get, if you have the two direction vectors of a plane A and B, you'll do the cross product of those, and that will give you the normal to the plane because the cross product will always give you a vector that's perpendicular to both of these. So that will you can get this directly from the vector equation of the plane because the two direction vectors are A and B. Figure out what your new vector n is, and that gives you A, B, and C for your equation. And then you just need, like I said, plug in a point that you know is on the plane to figure out what that d value is. Okay. So if we have two planes and the normals are called n1 and n2, they're only going to be parallel if the normals are scalar multiples of each other. So that should make sense. And they're only perpendicular to each other if, I believe this should be n1 dot n1 is equal to 0. That's a mistake. And if we want to know the angles between planes, we just use the two normals of the planes, do the dot product on the top, divide that by the products of their magnitudes, and then take the cos-inverse of that. This comes directly from our very first lesson in geometric representation of dot product. Okay, now I've got this little illustration of the situation. Basically, you've got your plane in the blue parallelogram, and you've got a normal, the red line here, ABC, that's perpendicular to the plane. So that's how that's represented. I don't think we have to go through this. I mean, we're just basically finding the normal and then using the components A, B, and C to create our Cartesian equation. So let's keep moving ahead. All right, so we've got the point A is a point on the plane with a normal. So the plane has a normal, -2, 3, -1. Determine the Cartesian equation of the plane. Okay, there's two ways of doing this. I'll show you both, but I think one is by far the best method. So the first method's the one that I don't use, but I'm going to show you anyways. If I want to create a vector from A to any other point, and I'll call it point X, Y, Z. Might as well put that here. If I want to create that vector, it's going to be X minus 3. So the components of that vector will be X minus 3, Y minus 4, and Z minus -1 or Z plus 1. And I know that AP, if I dot producted that with the normal, I will get 0. Okay, just by the definition of the normal. So the point XY is also on the plane along with A. So when I find the direction vector AP, that direction vector of the plane will be perpendicular to the normal, so the dot product is 0. Okay, so now if we did the dot product of the two vectors, with AP and N, we will get -2 from here times the X component here, so X minus 3, and then plus 3 times Y minus 4. So this is just a calculation of the dot product, plus, well, that would be minus 1 times Z plus 1. So that's the formula for the dot product, and that will equal 0 because that's the dot product, and we know it's equal to 0. So if I simplify this, I'm going to get -2x. Well, I'll just skip to the summary here. -2x plus 3y minus z minus 7 equals 0. So that's pretty much the Cartesian equation. The only thing that's a problem, and this was something we did in grade 9, we like all the ABC values, the coefficients of these, to be integers, and we really want the leading coefficient to be positive. So I'm just going to do a minor fix to that. If I want to change that to positive, I can just multiply the whole equation by -1. It's basically flipping all the signs. Okay, and this is the Cartesian equation I'm going to use. So I basically multiplied this by -1. Okay, just because mathematically we prefer that leading coefficient to be positive. Okay, so that's the way I don't do it, but you could. Now, since we know that's the normal, well, we know just about we know 3/4 of the equation, because that's my A, that's my B, and that's my C. So if I make the equation, it's going to be -2x plus 3y minus 1z. What we don't know is the d value, so I put a plus d equals 0. So now all I have to do is figure out what the d is, and I do this by subbing in the point that's given to us, 3, 4, -1. So I get -2 times 3 plus 3 times 4 minus -1 equals, well, if I put the d over here, it'd be -d. Okay, so then I get 7 equals -d but I really want d, so multiply both sides by -1. D equals -7. Okay, so now I'm going to just replace the d with -7, so I get -2x plus 3y minus z plus d, so that's -7 equals 0. And you can see, well, basically the same equation as that. And again, I'll do the multiply by -1, so I get 2x minus 3y plus z plus 7 equals 0. Just do that fixed to fix the negative leading coefficient. So you can see both methods give us the same equation. I think this is more work. You can see why it works, but why not use the fact that you know that the normal gives you the values of a, b, and c. Okay, example 2 says determine the scalar. So scalar is another word for Cartesian, if you see that in the textbook. If you see scalar equation, it means Cartesian equation. So we'll continue to use Cartesian. Determine the Cartesian equation of the plane containing the points B, C, and D. Okay, so we sort of did something like this on the last lesson. We actually created two direction vectors from those 3 points. Okay, so I believe, which points did I use? So I used BC. With BC, I got a direction vector of 1, 0, 2. And then I did another direction vector. I didn't actually write down what I used. I used I used C and D for this one. So C, D, B, C. So if I use C and D, I get direction vector -4, 2, -3. Okay. Now we want to create the Cartesian equation of the plane. So we need a vector. We basically need the normal of this plane that contains these 3 points. So instead of creating equation of the plane first, there's no point. What we want to do, we don't want to create the vector equation, although we could. What I want to do is do the cross product of these 2 vectors I just created, which are 2 direction vectors of the plane. If I do that, do the cross product, I get -4, 5, 2. And remember, the cross product of these 2 vectors of the plane gives me a normal. So this is equal to n. So these are my a, b, c values. So now, just like I did in this method, I use these values to create part of my Cartesian equation. So -4x plus 5y plus 2z plus d is equal to 0. And I have a choice of 3 points I can plug in to get my d value, and it will all give you the same d value, so don't worry about picking the easy one. I'm going to pick C. So I'm going to sub in 0, 1, 1. So -4 times 1. Oops, that's a 0. -4 times 0 plus 5 times 1 plus 2 times 1 plus d equals 0. So I get -5 plus 2 plus d equals 0. And that works out to -3 plus d, so d is equal to 3. Okay, and so now I've got my value of d. So my plane, I guess I could go back to using pi again. My plane's Cartesian equation, -4x plus 5y plus 2z plus 3 equals 0. But I've got the same problem with the negative sign there, so I'm going to fix that by flipping all the signs, which is essentially multiplying by -1. Okay, and there's my, I guess I'll put my pi down here. There's the equation of the plane that I was asked to find. Okay. So there's two different ways of creating the equation of the plane, but we use normals in both situations. Okay, example 3 says determine the vector and parametric equations of the plane whose Cartesian equation is given there. Okay, so this is going the opposite direction. Our first question, they gave us the vector equation, and we were asked to create the Cartesian equation. So now it's the opposite. Here's the Cartesian equation. What's the vector equation? So the way we're going to do this is similar to something we did in the last lesson. I need to find 3 points that are on this plane. Okay, and the way I'm going to do that, slightly different than what I did before, because I'm not using scalar multiples here. So I'm not going to just pick arbitrary values of s and t like I did before. But I do see that I can do something here. I can rearrange this equation to isolate x. So I get x is equal to 2y minus 3z plus 6. Once I've done that, now I can pick arbitrary values for y and z to create the associated x value to make this equation correct. So again, I'm going to create a little matrix here. So this time I'm just going to do 3 columns, x, y, and z. And I guess I should give one more row because I need 3 points this time. So my first row here will be point 1, point 2, point 3. Okay, so what I'm going to do is just pick some combinations of y and z and then figure out what x has to be to go with those y and z values. So I'm going to pick some nice easy values, 0, 0, 1, 0, and 0, 1. And when I plug this in, y and z being equal to 0, well, x has to be 6 for that combination. If y is 1, that's going to be 2 plus 0 plus 6. So x there would be 8. And if y is 0, but z is 1, so that would be negative 3 plus 6. So that would be 3. So I've got 3 points here, 3 points on the plane. Okay, and that's pretty much the way you have to do it. So hopefully you have a Cartesian equation where you can isolate for one of the 3 x, y, or z, and then just pick arbitrary values for the other 2 to come up with a combination of points. Okay, so now that I've got these 3 points, I can create 2 direction vectors between a combination of these 2 points. So I'm going to have my first direction vector called m1, and that's going to be using p1 and p2. So when I subtract, I get direction vector 2, 1, 0, subtracting upside down there. And my second direction vector would be if I do p2, p3, subtract that way, so I get 5, 1, negative 1. Okay, so I've got everything I need now. I've got 2 direction vectors to define the plane because I've taken 3 points on the plane. Now I need a point. I could take any one of these points to create my position vector. So here's my equation. R is equal to, I'll use the first point, 6, 0, 0, as my position vector to that point, plus s times the first direction vector, plus t times my second direction vector, 5, 1, negative 1. And there's my equation. So that's how you go in the opposite direction. If you're given the Cartesian equation, find 3 points through whatever method you can use. Once you've got those 3 points, create 2 direction vectors, and then directly from there you've got everything you need. Take one of these points to have your position vector and both of these with scalar multiples, and you're done. Okay. All right. going to finish off with some hopefully easier questions. And this is just a review. I think we've kind of covered this already. But if you have two planes 1 and 2, if they're perpendicular and their normals are n1 and n2, then the normals are perpendicular. If the planes are perpendicular, well then so are the normals. So therefore, the dot product of the two normals will be 0. Now, if in this case you've got two planes that are parallel, well, the normals n1 and n2 will also be parallel. I think it follows by logic. And therefore, their normals must be scalar multiples of each other since the normals are parallel. Okay, so let's use that information for the last example. So it says show that the planes, and we have Cartesian equations for plane 1 and plane 2, show that they're perpendicular. Okay, so since they're in Cartesian form, Cartesian equations, I know their normals. So I know n1 is equal to basically ABC, so that's 2, -3, 1. And the normal for the second plane is 4, -3, -17. So if they are parallel, then I should be able to do the dot product of their normals and get 0. So that would be my proof. So n1 dot n2. I can just do this quickly. So that's going to be 2 times 4 is 8. -3 times -3 is positive 9. And 1 times -17, -17. If I add those together, I do in fact get a 0. So therefore I can conclude that plane 1 and plane 2 are parallel. Okay, pretty straightforward. Just remembering that if the normals are perpendicular to the planes, if the normals of the planes are perpendicular, then the planes must also be perpendicular. And same thing for parallel. Now here we're going to show something like that. Show that plane 3 and plane 4 are parallel but not coincident. So parallel means they're going to have scalar multiples for their direction vectors, but they also have scalar multiples for their normals, but they won't have any points in common. So first thing we're going to do is, like we did last time, find the normals. So n1 is 2, -3, 2. Normal 2, I guess I should call them 3 and 4, but we'll keep going. 2, -3, 2. Now when I look at these two normals, I can see they're exactly the same. So I know that the normals are parallel. So that's the first aspect. They definitely are parallel. So plane 3 and plane 4 are parallel because their normals are parallel. Okay, now we still have to show that they're not coincident. And we do that, well, this one's pretty nicely laid out for us because you can see the A, B, C values are the same. Now, if their D values were the same, then they would be exactly the same line. If the D values are different, then they would be unique lines. Parallel but unique. Distinct, I think, is the proper terminology. So when I compare the D values, circling them here, I get D1 equals -1 and D2 is equal to -3. Well, obviously those are different. Those aren't equal. So therefore, plane 3 and plane 4 are not coincident. Okay. Now, this was kind of an easier question than it should have been. If those, if the normals were not exactly the same, probably what we would do is multiply one or both of these equations so that the ABC values were the same, and then compare the D values at that point. So a little bit of extra work if these were exactly the same and not just scalar multiples of each other. Okay, last question is determine the angle between the planes, plane 5 and plane 6. So both, again, in Cartesian equations. So I'm going to look at the normals, and I guess I'll call them normal 5 and 6 this time. The normal of equation 5 is 1, 2, 3. The normal for plane 6 is 3, 2, 1. And that's from the ABC values, of course. All right. Now, the equation for the angle between these, cosine theta equals, I have to do the dot product of the two normals and divide that by the magnitude of the two normals. Now, the original equation for this, for finding the angle, we'd put the direction vectors here, or any vectors. We're using the normals because basically the angle the planes make with each other will be the same the angle that the normals of those planes make to each other. So rather than try to come up with the direction vectors, we can do this directly from the normals. Now, we do need to get the dot product of these two. I guess I should call these 3 and 4, but I think you know what I mean. So if I do n5 dot n6, so I do the dot product, I get 3 plus 4 plus 3, that's 10. Now if that happened to be 0, that would tell us the angle between these planes is 90 degrees, and we would be done. We wouldn't even have to do this. But I'd say 99% of the questions, it's not going to be 90, so you actually still have to keep going. So cosine of theta is equal to 10. Now if I take the magnitude of these two vectors, remember it's the square root of the sum of the squares of these. So that would be 1 plus 4 plus 9, so square root of 14. This would also be square root of 14 because it's the same numbers. So it's basically square root of 14 times square root of 14, which is really 14. So it's the cos theta is equal to the cos inverse of 10 over 14, which is 44.4 degrees. Okay, and that's pretty straightforward, I think. Okay, so we've done this formula before. We just haven't done it using the normals. We always used it either using a direction vector of a line or direction vector. I guess we haven't used it with planes. So with planes, we'll always use normals. Okay, so that's it for the lesson. That wraps up this unit as well. So until the next lesson, take care. See you then.